All right, ladies and gentlemen, welcome. And this is chapter 26, where we are looking at chi-square tests. And in this particular video, we are going to be covering what's called a chi-square test of homogeneity. We have already covered the chi-square tests, goodness of fit tests. That was in our previous video on chapter 26. So there's a lot of things about chi-square stuff that we're not going to talk about in here. We're going to just jump straight into talking about this test. So the chi-square goodness of fit test was for a single variable, right? It's when we had the ball player example where we had this, we had a single variable of information, right? We had the birth months, right, of something over here, and then it was how many ball players were born in each month, right? Some number, some number, some number, some number. Okay, one variable. We do have a test that compares the distribution of counts for two or more groups of the same categorical variable, and that's called the chi-square test of homogeneity. And when I say two or more groups, you should be thinking back to like chapter 3 when we did contingency tables. You might remember that we did that group that was, let's see, it was alive and dead, and it was the Titanic survivors, right? First class, second class, third class, and crew. And we had a certain number of things in each one, right? This was the number of people that were in first class that lived, first class that died, second class that lived, second class that died, etc. We can do a test to determine if these two groups are homogeneous, meaning the same, right? Or we can do a test to find out if these four groups, these row groups, are the same. They're going to be the same test. It's called the chi-square test of homogeneity. So we do this test when we have multiple groups on the same categorical variable. So again, alive versus dead, that's two different groups for the same categorical variable, living and dead, all right? Or I guess the variable would be whether or not they live. So the statistic that we calculate for this test is identical to the chi-square statistic for goodness of fit. It is the same test statistic. However, what changes here are what we're in this test. What we're testing is instead of it seeing if this observed group meets the expected group, we're seeing whether choices are the same among different groups. So living and dead versus the Titanic. Okay. The expected counts are found directly from the data that we have, and our degrees of freedom is calculated differently. So we also have assumptions and conditions for this. They are basically the same as the previous ones. We have our counted data condition, again, which we don't need to check. We don't need to write this one down. We just need to check to make sure. We say this one because we want to make sure that this is the correct test, but that's not something that we need to like state for the AP test. The things that we do need to state are randomization and expected counts, with the caveat here that if we're not trying to generalize our results, meaning apply this sample to an outside population, we actually don't need this one to be random. Though, again, for the AP exam, we're looking at randomness here. The expected cell frequency count is the same. This is our sample size, right? Our sample size does have to be sort of large, but again, instead of it being from the sample, it's going to be based on what we have in our data. The expected count needs to be at least 5. So assumptions and conditions for this test basically the same. Our calculations to find the expected counts, what we're going to do is multiply the row total by the column total and divide by the grand total. I will show you guys that in a moment when we have our example. This test statistic is the same, right? It is the sum of all cells, where we take the observed minus the expected squared divided by the expected. Uh, Again, hand calculating this, you won't do it that often. We have technology to do that for us. Here's the biggest difference. The two big differences are finding the expected counts and this, the degrees of freedom. The degrees of freedom was, for the goodness of fit, n minus 1, right? For the Goff test, degrees of freedom was n minus 1. For this test, it's r minus 1 times c minus 1. So let's go just real quick, think about this in terms of our Titanic example. R and C stand for the rows and the columns. So this would be 4 minus 1 times 2 minus 1, which is 3 times 1. So the degrees of freedom would be 3 for this particular example. We take the rows minus 1 times the columns minus 1, and that tells us our degrees of freedom. We do need the degrees of freedom to find our p-value and for the Chi-Square statistic, but again, we're going to be calculating those using technology, so whether, how we use it is the same. However, I can tell you for a fact that there are multiple choice questions on the AP exam where the whole point is they give you a table and they say how many degrees of freedom is this. So you need to know this r minus 1 times c minus 1. I know for a fact that they have AP multiple choice questions where they're going to give you a table and they're going to say what are the expected counts of this table. And so we need to understand how to find the expected counts on this table as well. Typically, if you're actually just running the test, you just need to be able to run the test, and you can use technology for those things. So here's our example. Medical researchers enlisted 90 subjects for an experiment comparing treatments for depression. The subjects were randomly divided into 3 groups and given pills to take for a period of 3 months. Unknown to them, one group received a placebo, the second group received the natural remedy, St. John's wort, and the third group received the prescription drug Posrex. After 6 months, psychologists and physicians who did not know which treatment each person had received evaluated the subjects to see if their depression had returned. Hopefully you guys read this as they did not know what they received as being blinded, right? Remember way back, that's a nice review word to think about, being blinded. There were 3 treatments, just speaking about review, right? There's 3 different treatments for one factor. So there's 3 treatments, the placebo, the St. John's wort, and the Posrex. They were randomly assigned to those treatments. So we've got good experimental design going on here, okay? And then here's our data down below, right? So the placebo, 24 had depression return, 6 of them had no signs of depression. The St. John's wort, 22 had depression return, 8 of them had no sign of depression. And for the Posrex, 14 of them had the depression return, and the 16 of them had no signs of depression. So the question here is, are the occurrences of depression the same across all 3 groups? Okay. So again, it's this question right here, are the occurrences the same across all 3 groups, that tells us that this is a test of homogeneity. The next test that we're going to do in the following video from this is the test of independence. And the only way that you can really tell the difference between the two is the question that is being asked, because the test of homogeneity and the test of independence are actually exactly the same. The only thing that changes is what question are we asking, okay? So here we're asking, is the occurrence of depression the same across 3 groups? So it's the test of homogeneity that we're using. So there's our null hypothesis. Let's follow through our, our hammock method of looking at a test. The null hypothesis is the rate of reoccurrence, is the rate of reoccurrence is the same for all 3 treatments. So we're making an assumption here that the rate of reoccurrence is the same. Again, you should read the null hypothesis as a statement about equality. The rate of reoccurrence is the same for all 3 treatments, and the alternative hypothesis is going to be the opposite of that. The rate of recurrence differs for some treatments. And again, you should be reading that as The alternative hypothesis is a statement about not being equal. Also remember, with all of our tests of Chi-Square, the null and alternative hypotheses are are statements. We do not do them symbolically. We do write them out completely as statements. So there is my ha and hammock. So let's look at assumptions and conditions. Do we have the counted data? Yes. Let's look at our expected counts. Notice that I'm not doing the randomization piece here. I'm just looking, although we could say that they were randomly assigned to treatments, right? They were randomly assigned to treatments. So we do technically have some ability to generalize in this one. They were randomly assigned to treatments. But we do want to talk about expected counts here. So there's a logic behind the expected counts. The logic being, if we're talking about all three of them being the same across the three occurrences, we would expect this total to be proportionally split across each of the categories here. So notice that we have what we can do to find that is first of all, if this is 60, then we kind of know that they need to be evenly distributed here as part of our expected counts. So that's going to be 20, 20, 20. Okay. But again, the way that you can find that out is you can do what am I doing? You can take the total down here, the column total, and divide it by the total here, which is 1/3, right? 30 divided by 90, which makes 1/3. And then you can multiply that by the 60 here. 1/3 times 60 makes 20, so all of these need to be 20. In the same case here, we can take this same bit and multiply it by 30. That's 1/3, 1/3, 1/3. Right? All of these make 1/3 when we divide them by 90. And multiplying this by 1/3, this one, because this is 30 over 90, this one should be 1/3 of the total, so that's 10. This one should be 1/3 of the total, so that's 10. And this one should be 1/3 of the total, so that's 10. So we're comparing the totals down below, the column totals, to make sure that they are proportionally the same as what we have over here. If this was like 40 instead of 30, then we would have 40 out of 90, and then we would multiply for this one we would multiply 30 by 4 over 9, and this one by 4 over 9 as well to find that one. So we're just taking the proportions of the totals and multiplying it by the other total to find each of what these ones are going to be. So then our expected count, do we have enough? So remember, we need to have 5 in each cell. We can say the smallest cell, the smallest expected cell is 10. Therefore, the sample size is large enough. Actually, I'm sorry, I skipped a sentence that we should say in there. The sample size, the smallest expected is 10, which is larger than 5. We need to state that in there. Larger than 5, even though that's obvious. So the sample size is large enough. And that's the last of my assumptions and conditions. So as we finish writing about our assumptions and conditions, we want to write the statement that says, and I'm going to do it up here, conditions have been met. For a Chi-Square Test of Homogeneity. So assumptions and conditions are met for the Chi-Square Test of Homogeneity. Let's go talk about mechanics. And to do the mechanics, again, we're not going to hand calculate this. Let's go ahead and use our calculadora on this one here. So the I don't want to do that. Come back over. We want to have that open. There we go. So notice that the data that we're given here is in the form of a matrix, right? This is a matrix. And so when we're actually doing this test statistic, we're going to be using the matrix functions of our calculator, which you will see is under the matrix function right here. So if you hit second and then the inverse there, or not inverse, the reciprocal, but never mind. These are your matrix functions. So the first thing that we need to do is enter the matrix. So swallow the blue pill, and then we'll get ready to go. Once you've swallowed the blue pill, go over to edit, because this allows you to put the data into the calculator here. So we're going to edit matrix A, and this matrix, remember, we go rows by columns. So this is a 2-row. Nope, I lied. Did I lie? No, I didn't lie. This is 2 rows, 3 columns, so it's 2 by 3. And then we simply enter the values from the matrix that we have over there. And that's 8, 8, 6, 8, 16. Boom, there we go. There's my matrix. And we're comparing the observed minus the expected. Now, something I want to show you guys that your calculator does that's really special. Once you have the data matrix input here, if you go to your tests, and your tests, by the way, are the same as where the other ones are, right? Stat tests. The test we're looking for is this thing called the Chi-Square test. Now, on a TI-84, TI-84s do not have, TI-84s have the Chi-Square test and the Chi-Square goodness of fit test. A TI-83 has a Chi-Square test, but not the Chi-Square goodness of fit test. So this is the test, even if you have an 83, that you can still use. So when you hit enter on this and the wizard comes up, notice that it's looking for 2 matrices. We're looking for the observed matrix and the expected matrix. Now, if you will recall correctly, I only put in an observed matrix. I entered no expected matrix, right? See, I'll prove it. Look, there's nothing in matrix B right here. There's no data there. But if you go over to this test and you come down here, you do Chi-Square test, and you say, hey, calculator, look at matrix B to find your expected, your calculator is so smart about finding the expected values that when you hit calculate, it still does this, even though there's no data for the expected there. That's my Chi-Square statistic. That's my p-value. So if I go back to the matrix now, look, they entered, the calculator when I did that, entered that matrix for me. If you go down here and you hit B and enter, there's my expected values matrix. They did those things for me. Like, my calculator is so smart that it can find the expected values matrix for me. Now, I don't want you to feel disillusioned that you can just do this and not know how the mathematics works to do that. Because like I said, the multiple choice questions will often give you something where you can't use a calculator to enter this stuff. So be careful. Please still understand that you need to take the proportion to find the expected value of this cell. I take the proportion of 30 over 90, and then I multiply that by the row total over here. You have to do that, know how to do that still for the AP exam, right? Don't start fooling yourself. But if you're simply needing to do the test, okay, to do the test of homogeneity, you can use this to create the expected matrix for you. So that is a super nice feature of your smart technology that does those things for you. I'm gonna just go back up here and hit this chi-square thing again because I didn't write my information down. That was a poor choice. Do it again. There we go. So my chi-square is statistic is 8.4, and my p-value is 0.014. And so going back into my presentation here, assumptions and conditions I did, there's my mechanics. The things that we want to make sure that we record on this stage, again, this is for the AP exam. We want to make sure that we record that my chi-squared statistic was 8.4 and that my p-value was 0.014. And that's my mechanics step. Let's just talk conclusion here. I can say because, wait a second, p-value is less than 0.05. It wasn't less than 0.05. Something's wrong with my presentation. Or maybe, did I enter everything correctly? Let's double check this. Because it shouldn't say that. That's not what I got. Did I mess something up? 24, 22, 14, 6, 8, 60. No, I did it right. I think my presentation might be messed up. Wait, I'm sorry. I'm having a total space cadet moment here. Okay, so sorry, you should just maybe like ignore the last 10, 20, 30 seconds of this presentation. 0.014 it does in fact is in fact smaller than 0.05. Woo! I don't know what is wrong with me today. 0.014 is smaller than 0.05, so nothing's wrong. Ignore the last 45 seconds of this presentation. Because p is less than 0.05, we reject the null hypothesis. There is strong evidence that the tested treatments are not all equally effective in preventing the reoccurrence of depression. It appears that people who take the prescription drug Prozrex are more likely to remain free of the disease than those who took a placebo or the natural remedy St. John's wort. Okay, that's better. Didn't make a mistake. We're all good. All right, so that last bit in the conclusion where we talked about the Prozrex being more likely. We got that because we looked at the residuals, and it's always a good idea to just look at the residuals to see which one of the values is a lot more. Having more of an effect on the overall p-value. So I won't go. I'm not going to go into the details on this one here. But you can see that when you calculate this observed minus expected, you can see, oh, not this one. Man, this last 5 minutes of this is just going to be awful. When you calculate this one, you can see which of the 6 different cells there is having the biggest effect on the chi-square statistic. And in this case, the Prozrex ones were having the biggest, or in this case, the least effect, whereas the main differences came in the St. John's wort and the placebo. All right, we're going to end this right now before I manage to mess it up anymore. So thank you for watching. If you've got questions, leave them in the comments. I'll be able to help you out or message me in some way. Thank you for watching. Bye.